Welcome to this video where I'll be talking about electric field by a thin spherical shell. It's a very important concept and not a lot of people understand it fully because of the difference in the two cases. So I'll be discussing that in detail. If you do like this video, please do share it with your friends and do not forget to subscribe to the channel. Let's get started. Okay, first things first, like every video that we've done on this topic, first we need to understand surface charge density. Surface charge density is simply the amount of charge per unit area, because we're talking about the area of a shell or a sphere or a plane and whatnot. So that's where surface charge density is. Obviously this will be in unit area, so take care of that. So once we have this, there are essentially two cases in a shell. In a spherical shell, there are two cases that we need to consider. Let's first look at a shell and then I'll tell you why are there two. So let's imagine this is a spherical shell. Spherical shell essentially means that the inside is hollow and there is only a thin layer of metal sheet, which is what the shell is made up of. Obviously, if this is a sphere, there will be a center. This center is just a is just for the radius and stuff, but it is not actually present or made up of anything, right? This is, say, R is the radius of the shell. Now why are there two cases? There are two cases because the charge is on this surface. This is the metal surface on which the charge resides, and so my point of electric field can be either outside the shell, which is here, or it can also be inside the shell, which is here. And I want to look at both these cases, outside the shell and inside the shell, to figure out which one, what are the results for each one of them. Okay, so let's first talk about outside the shell. If I'm going to take an outside the shell thing here, let's take the distance of this point as r from the center, of course. Okay, now just like every other thing that we've taken, what is the Gaussian surface that I have to encapsulate, right? Obviously the Gaussian surface that I'll encapsulate here is going to be another sphere. Why am I taking a sphere and not a cylinder or a square or whatever, or a cube or a cuboid? Because I want to see the effect of the entire shell at this point, and the electric field at this point and at this point and at this point at equal distances from the center will be equal. That is what the symmetry of spherical shape allows us to tell, right? Every electric field at this point and this point and this point and this point, all of the points will have the same electric field due to the symmetry of the spherical shape. That's why if I take a Gaussian surface which is spherical in shape, you can see that it encapsulates the entire shell inside it. It encapsulates the entire shell inside it. Okay, so once we have understood that, let's try to see what's going to happen. First, we need to figure out how much is the flux which is moving out of this Gaussian surface. So flux is equals to E into A. What is the E? That is exactly what I want to find. What is the A? A is the area of this surface. For a spherical shell, that becomes 4 pi r square. Okay, so 4 pi r square, small r because it's an outside sphere that we are talking about, that is the area, the surface area of that sphere. So this is the total flux that will be moving out. As you can see that the whole charge, all of the charge inside is encapsulated in. So we'll look at that. So the flux will be equals to Q upon epsilon naught. So I can write E into 4 pi r square is equals to Q upon epsilon naught. Now, how much is Q? Q is simply, Q is the total charge on this shell, and Q is equals to sigma into the surface, right? So, sigma into 4 pi capital R square upon epsilon naught. Why? Because Q is the total charge, and total charge divided by area, total surface area is what sigma is. So sigma into the total area will give me Q. So that's what I've replaced it with. Therefore, now I get E as, I will take it down, 4 pi cancels out, it becomes sigma r square upon epsilon naught into small r square. Okay. Now, I can actually revert this back. I want to show you both the sides, but if I multiply it by 4 pi in both the numerator and the denominator, I can do that. Why? Because the ratio of 4 pi upon 4 pi is 1, so I can obviously everything can be multiplied with 1. So I get again the same thing, sigma 4 pi r capital R square, which is what? Q. So I can then just write Q upon 4 pi r square, 4 pi epsilon naught into r square. This is what? This is the Coulomb's constant. So this is essentially a form of the Coulomb's law. It essentially gives me the same result as the Coulomb's law for a point charge. That means the spherical shell acts like a point charge when I am talking about and point to find out the electric field outside of that shell. A very, very important result. Okay, it acts like a point charge, as if all the charge is condensed in the center and it is simply just acting like that. Okay, very important result. Now, the second part of this, which is inside the shell, equally interesting. Let's say this is the point I want to figure out. I will again make a spherical shape over here. The distance here is also small r. This is inside the shell. Now we are talking about this point inside the shell. Again, I have taken a Gaussian surface of sphere, again because the symmetry allows us to do that. When I take the Gaussian surface as this, how much is the charge which is encapsulated by the Gaussian surface? 0, right? Because there is no charge inside, which gives me the flux as 0. Why? Because flux was equals to Q upon epsilon naught. Q is 0 in this case because there is no charge encapsulated, which implies, if flux is 0, which implies the electric field inside is 0. It's as simple as that. Just logic. Okay, the electric field inside the spherical shell is 0. Now, this is an exciting result. Why? Because this allows the spherical shape, or rather any metal shape shell, to be used as a protective layer for for electronics inside, right? It protects from outside electromagnetic pulses as well, right? So it is a very important protective gear, especially for expensive products and materials made up of electronics. Okay, so this result single-handedly is used for that case. So I hope you liked today's video, and if you did, please do like, subscribe and share the video so that a lot more of your friends can know about us and learn better, especially the physics concepts. Okay, so do tell me in the comments below about what topics you would like me to cover next, as well as any questions or doubts you might have. I'll try to get to them as soon as possible, and you can subscribe to the channel and do not forget to press that bell icon so that you get to know when I'm putting up or Atray Sir is putting up the next video on our channel. So I'll see you soon.